We're going to talk about Ampere-Maxwell Law today, and this is one of Maxwell's equations that we're almost there. We're almost done with electromagnetism. And first, let's talk about Ampere's law, and then we'll talk about how it got modified a little bit by Maxwell. Okay, so Ampere's law basically says this: B dot ds equals mu naught times I enclosed. Okay, and this is pretty scary looking, but remember what it means. It really is saying that, hey, the source, it comes from the Biot-Savart law that says that the source of magnetic fields is a current. What creates a magnetic field? A current does. So this says, hey, if you take a current and you surround it with a loop, a closed loop, if you take the dot product of the magnetic field with that closed loop, it will be equal to this constant of nature, mu naught, times the current that was enclosed by the loop. It's kind of a weird law, but hey, it works. And so this was kind of the law of the land for a while, but then good old Maxwell, he started looking, well, what about this? What about this? What if you had a current like this, and so you have a wire with a current flowing through it, and you say, oh, okay, well, look, I surround this with a closed loop. Here's my Amperian loop, as we call it. And you say, oh, okay, well, B dot ds, and you go, okay, B is going to be a constant, right? This current is going to create using the right-hand rule, it's going to be creating a magnetic field line in a circle. So we just plop our loop down on top of that magnetic field. So this just becomes, so B is a constant, it comes out of the integral, and then the sum of the closed loop is just 2 pi r, just the circumference of a circle, right? And then you get mu naught I, because I is the current that's enclosed, and of course you get the magnetic field that mu naught I over 2 pi r, where r is our distance there from the wire, right? The radius coming out of there. Well, then Maxwell said, but look, what if you hooked up to this a capacitor? Okay, now really start thinking and waking up here, because this is the killing part. Let's put a capacitor in here. I'll leave some room in there, just to make it easier to draw. Well, what happens there? Because if I draw my Amperian loop right here, here's my loop, there's no current through that loop anymore. Yeah? There's no current in that loop. And yet, what we find is that if we force a current to flow, through here, what's going to happen on this capacitor? Well, it's going to build up charge, but here's what we get. We still get a magnetic field there that's identical to the magnetic field here. Maxwell said, hey, something's not finished here in our thinking. Yeah, if I've got current going through this wire, I can use Ampere's law to figure out what the magnetic field is around there. But look, there's something going on here where it acts like there's a current in there, even though there isn't. There is no flow of charge across these plates. There isn't. But what is happening between here and here? You have a changing electric field. And here's the killing part, okay? Here's our target. It turns out that a changing electric field acts like a current. If you have a changing electric field, that creates a magnetic field. A changing electric field will create a magnetic field. This is one of the most profound ideas in electromagnetism, and it unites electromagnetism. This is a big idea. So what he said, well, look, let's suppose we start at t equals 0. And what we can do in our imagination is hook this up to a voltage source. I'll just call it V like this. It's not a battery. Let's hook up a voltage source so that it makes the current, at least for a little while, it forces the current to be constant. So that as the charge builds up on the capacitor, we'll increase the voltage so that the current will be constant. That's kind of a thought experiment, okay? So we have a steady current here. Now, so what's happening here is that we're building up a charge. And as we build up a charge, we build up an electric field. And we increase, so we're increasing the amount of magnetic flux through that loop. Well, let's see. What happens is that this changing this changing amount of electric flux acts like a current, and we end up. Well, this is just. Oh, okay. I think I remember. So let's look at what's happening here on this plate. I'm going to surround this plate with a Gaussian surface. So here's the plate, and here it is building up. Here's the charge that's on that positive plate. Here's my Gaussian surface, okay? And what I'm going to do is this. I'm going to say, okay, E dot dA equals the charge enclosed over epsilon naught. Well, what is this? Well, I'm sorry, this is also equal to the total amount of electric flux in the capacitor. Okay, so if I surround this with I'm going to surround the whole capacitor here, at least the left side of it, with a Gaussian surface, okay? And what that, and I'm going to use Gauss's law, but what I'm really doing is I am figuring out how much electric flux is in there. Remember we did that? Electric flux, careful. Electric flux is equal to the electric field times the area. Okay, so this is, now I'm going to take a look at this. But what's happening as the current comes in, what's happening in there is that I am adding charge to this at a certain rate, right? And if I add charge on this plate at a certain rate, that means that I'm going to be adding flux at a certain rate, because the flux is directly proportional to the amount of charge on the plate. So here's what I'm going to do. I'm going to say, okay, the electric flux is equal to the charge on the plate, I'll just call it Q now, over epsilon naught. I'm going to take the derivative of this. Okay? Now, don't get freaked out by math. When I take the derivative of it, I'm just saying, at what rate is it changing? Okay? Stay with me now. So this is d phi dt is equal to, well, here we have a 1 over epsilon naught, right? 1 over epsilon naught. And then what have I got left? I got the charge on the plate, Q. But I'm going to take the derivative of that, and that's going to be dq dt. So the rate at which I add electric flux to my capacitor is equal to the current that's coming into that capacitor, right? What is dq dt? It's the current that's coming into the capacitor. Well, the current that's coming into the capacitor, I'm going to call that, for some strange reason, well, I'm just going to solve for it. Am I still on screen? Yes, okay. dq dt is equal to epsilon naught times d phi dt. Okay, if you can understand this chain of logic here, you're doing really great, okay? And so I want to go through it again. But now this term right here, well, what is dq dt? Let's think about what dq dt is. Here's my capacitor, and the drawing has gotten all ugly, but here's my capacitor, and look, I got a current flowing in it, right? Well, what is that current doing to my capacitor? It's adding charge to one of the plates at a certain rate, which is right here. But what does that do? That changes the amount of electric flux at a certain rate. And this epsilon naught is just my constant of proportionality. It just makes the units work out. It's just a constant in nature, right? This relates current to magnetic flux, or charge to magnetic flux. So we call this, well, the book will call it I sub d, which has the unfortunate name, and I don't really know where it comes from. I suppose I should. It's called displacement current. Displacement current. That's the name of it, and I'm sorry for that name. Is equal to epsilon naught times dE dt. But what it says is this: if you change the rate at which you change magnetic flux times epsilon naught, well, that acts exactly like a current as far as creating a magnetic field is concerned. So what we have to do, in other words, this acts just like a current. This behaves exactly like a current between these plates. So when I surround this with an Amperian loop, this changing electric flux, I keep calling it magnetic flux, I'm sorry. This changing electric flux acts like a current and creates magnetic flux around it. And so what Maxwell, who figured this out, says we need to add something to Ampere's law. And it's this. Well, we'll say mu naught I enclosed. But this is if you're over here and you're just surrounding a current. Plus mu naught times the displacement current. Or this is acting just like the current. And this is called the Ampere-Maxwell Law, because Maxwell added something to it. Now, let me just say that in this class, we never use these two parts together at the same time. I want you to look up here. Okay, think in this wire. We have a current going through this loop, don't we? But is there a capacitor there? No. Is there any changing electric flux in here? No. So this part is just 0. And we just have regular old Ampere's law. But if we have a capacitor, there's no charge flowing through it, right? There's no transfer of charge from here across the plate, unless it's like failing or something and smoke is coming out of it and it's bad. No, there is no flow of charge across the plates of a capacitor. But charge is building up on one of the plates. We're adding electric flux across those plates. And therefore, we have what we call displacement current. I'd prefer to call it a electric flux current kind of stuff. All right? It's acting as if it's a current. So we have this. So this is 0, and we have this. But we can still use Ampere's law. Now, last thing I'm going to say. This idea right here, look at this term right here. Now, we have mu naught and epsilon naught, and this is related to the electric constant, and this is related to the magnetic constant. Why don't we just use K? And why is we have mu naught over 4 pi and all that kind of weird stuff in the Biot-Savart law? Why do we call it this? I'm telling you this right here. This is cool. Now, I'm just going to tell you this. You're not going to understand this yet, and it's okay. I understood it for a little while, but it's been so long since I studied it. I just remember it. If you do this, 1 over the square root of mu naught epsilon naught, you get the speed of light. You get the speed of light. Now later on, Maxwell used that to figure it out, and I'm just going to use this as a teaser for you to take more physics, okay? Because it's not on the AP outline. You've got enough to study as it is. I'm just telling you that there's something really cool in your future if you study more physics. Okay, we're not quite there yet, but the speed of light is embedded in electromagnetism. And it turns out that light is an interaction between electric fields and magnetic fields. Okay, so I really hope that that kind of stuff gets you going, because this leads to some of the coolest stuff that I've ever understood in my life. I remember I took an advanced E&M class in college, and we were doing this stuff with Maxwell's equations, electromagnetism, and out popped relativity. And this is how Einstein figured out his theory of relativity. And I remember doing this lecture, and I felt like my head was going to explode, but it was out of a sense of like that eureka or that epiphany you get when you understand something. And I go, oh my God, I understand what Einstein did. Now I don't understand it now, because it required, the fog rolled back in shortly thereafter. But I do remember that feeling of understanding it, and it just being like this feeling of just pure joy. So I'm not sure Ned is there yet, but no, it's okay, Ned. But it is very cool. So it's out there in the future. But for right now, I just want you to understand that, hey, moving charge currents create magnetic fields, and Ampere's law describes how to calculate what that magnetic field is. But across a capacitor, adding electric field lines across here, increasing the amount of flux at a certain rate, acts just like a current. And so therefore, this is leading us to the idea that electric fields and magnetic fields are related. And that relationship unites those two fields of study. Anyway, that's it for now.